Welcome to the office. We want to take a look at some properties of homomorphisms now. And we want to start off with a definition or a collection of definitions, rather, that are related to functions or mappings. So let's let phi be a mapping of a set X into a set Y. So that's just saying we have phi from X to Y. And we're going to let A be a subset of X and B be a subset of Y. Okay. The image of A, so this is a little bit different than maybe what we're used to. Chances are we've seen this sort of thing before too. But what we're saying is that phi of A, the image of a set, is a set. And it is simply the collection of things that we can get out, right? The image of the set is, oh, look, the image of A from A, boom, that's in the image of the set. Not too surprising. If we consider the set of all images, right, the images of all elements, then that, of course, is the range of the mapping. We have X, and we have Y. I have some elements over here. I have some elements over here. The range, of course, would just be this collection of elements. If I had something more than that, then I could say the image of this set is that set. Well, those are both of those definitions so far. And then if I wanted to go the other way, I could say, oh, well, if this is a set in Y, then what gives me that is the pre-image or the inverse image. And the thing is here, if I wanted to, I could have things repeated. So when I look at the inverse image of this, it can give me back more things than were in the set X. So this gives us image, range, and inverse image. With that in mind, we can take a look at some properties that really shouldn't be too surprising. Most of these properties of homomorphisms are things that we've already talked about because isomorphisms are examples of homomorphisms. Those are homomorphisms that just happen to be one-to-one and onto. And many of the results that we had for isomorphisms were not dependent on the fact that it was one-to-one and onto. So, some of them were, but not all. So if E is the identity element in G, then the image of the identity is the identity in G prime. Yeah, right. That's the same thing that we had before. If A is in G, then the image of the inverse is the inverse of the image. Well, that's no surprise because I want to have that phi of A, or I need to satisfy the homomorphism property. So if I have phi of A inverse, that's phi of E, of course. That should be phi of, or that should be E. That should result in E, the identity in G prime. But in order for that to happen, then I need the image of A and the image of A inverse to be inverses of one another. Therefore, we must have that this is phi of A times phi of A inverse. Because I need it to be equal to E prime, the identity in G prime. So if H is a subgroup of G, then the image of the subgroup is also a subgroup. Cool. If K prime is a subgroup of G prime, then the pre-image or inverse image of K prime is a subgroup of G. So if we have G and G prime, here are our sets. If I have a subgroup, it maps to another subgroup. If I have a subgroup, its pre-image or inverse image is also a subgroup. All right. Now we want to talk about what we call the kernel. the kernel of a mapping is simply the collection of elements that get mapped to the identity in G prime. So we are looking for the subgroup, the inverse image of the identity in G prime is all of the things from G whose output is the identity. Again, if we wanted to, that nice set imagery here, I have G and G prime. If this is my identity element in G prime, what I'm interested in observing is which elements map to E. So here, if I say this is A and this is B, then the kernel of phi is the set AB in this nice little image here. All right. So we have some basic ideas of the image of a group or image of a subgroup, inverse image of a subgroup, and this particular one that we're interested in, right? E itself is a subgroup. It's a trivial subgroup, and therefore its inverse image must also be a subgroup of G. So the kernel is right, it is a subgroup. And we understand that from number 4 here in the properties. All right, I think that's all that I really wanted to share. Oh, there is one additional detail that I want to make sure that we are following along with. I think this is something that we had before, but if we have, again, if we have that phi is a homomorphism, then phi of a to the n is equal to phi of a to the n. Okay? That's just an application of phi of a is phi of a, phi of a. And then you can apply that inductively to get this, essentially, is what we're looking at there. All right, that's all that I wanted to share. Let's take a look at a couple of examples. And let's take a look at a couple of examples in our next video.